My presentation is going to be starting from the basics. The intention of this presentation is to give them the basic concepts in estimation and testing hypothesis problem. In many places, that for sample size calculation, epidemiologists use only one formula, that is for 4 pq by d square, which is very shocking. And therefore, we need to give the young statisticians who did not have an opportunity to work in the hospital settings and so on, that this will help them to understand what we are talking about as a hypothesis, how to reject the hypothesis, implication of not rejecting the hypothesis, alpha error, beta error, and power calculations. And then we'll move on to the superiority, non-inferiority, and the equivalence trial. In some occasions, I would reiterate what Shrikant has presented. So therefore, the concept gets clear again. We'll go slowly. The process, there are some technical issues. I'll demonstrate using the software which we have developed. It's called the McMaster. Most of you have that McMaster with you. Please have them. If you have the laptop access now, just follow me what I'm doing. It will be a kind of discussion-oriented practical session. There are two main divisions in medical research. One is estimating a quantity, a parameter, or a statistics, and hypothesis testing. So first I need to understand what is my problem. Am I going to estimate something, or am I going to compare 2 or more groups? That has to be sorted out. The estimation problem works around the concept called a 95% confidence interval. Whereas the hypothesis testing problem compared 2 or more groups, therefore the process of making a decision one is better than the other deals with the 2 kinds of error, alpha error and beta error. So we need to understand implications of this error and not rejecting the null hypothesis and so on. So when I say estimation, broadly the estimation is an important concept, that you wanted to know what is the incidence of drug resistance in a study. So therefore it is 5%, 10%, or 15%. When you provide a statistics, you wanted to provide a variability around that statistics. That is called a 95% confidence interval. That is all you do. This is what your main goal. There is no comparison here involved, just to estimate, so for example, incidence of suicidal ideation in women experienced spousal violence. If there is a, is it a 10%, 20%? What is the confidence interval about that data? So this is, so if I say 10%, it's called a point estimate. When somebody repeated the study again somewhere else, it cannot be exactly 10%. There is a variability around this 10%. So in order to explain that variability, we provide 95% confidence interval. Similarly, hepatitis B infections after renal transplant. So therefore, this is a point estimation, that numerical value from the sample will be used to represent the population parameter. So therefore, if I take all the transplants, renal transplant which take place in India, and what is the infection rate, hepatitis B infection rate, that is a goal to find out. Let us say that is the population. Population is all renal transplant which happened in India this year. So therefore, when I say it is 10%, it may not be exactly 10%, it may be 12%, 13%, and so on. So in order to say that the variability, the parameter is likely to fall within this limits, lower limit and upper limit, then we establish the confidence interval using the standard error concept. Say, for example, a study which we did in 1998 said the prevalence of HIV was 1.8%. Now the question is, if this gets repeated by various organizations, will they get 1.8%? Therefore, you are asked to provide what is a 95% confidence interval. The 95% confidence interval, what does it suggest? That it suggests that if there is a parameter, there's a single value, which is a true value, about the HIV prevalence, that is likely to fall within these two limits. If I establish a lower limit and upper limit, 95% of the time, the confidence interval likely to cover or the parameter fall within these two limits. 5% of that time, it is expected to go away from these two limits. Okay. Please remember, this is 95% confidence interval. The complement 5% is many times noted as alpha error. It is not alpha error. The error concept doesn't come here at all. It is the 95% coverage of the two limits covers the parameter 95% of the time, and therefore 5% of the time it goes outside. The wrong interpretation of 95% confidence interval is that as any number of times that you repeat the study, whatever the estimate you get is going to fall within this limit 95% of the time. It is a wrong concept. You need to say the whole purpose of the study is to estimate the population parameter. Therefore, the confidence interval is likely to cover the population parameter 95% of the time. Please remember this is very important. Therefore, we are not talking about that error concept so far. How do I calculate that confidence limits for the beginners? You all know the statisticians. There's a point estimate. If it is a HIV prevalence is 2%, then you put 2 here. How confident we want it to be? 95% confident. The Z statistics and the normal distribution corresponding to 95% area probability is 1.96, approximately 2, and multiply that 2 with the standard error of that statistics. That gives you lower and upper limit. So this is very important. But practically speaking, when you decide a sample size, someone wanted to do this. Say, I am doing I wanted to estimate the blood loss when I do knee replacement surgery. How do I find that out? So the question is that how many patients do I study to estimate exactly or very correctly the blood loss, mean blood loss if I do 10 surgeries or 20 surgeries. Or so the goal is that to see what would be the average value of the blood loss. That is a big question you have. So you need to have some kind of variability data and about that statistics and how confidently you want to estimate this statistics. So this is something in a standard normal distribution. Please remember, this is a very important concept. This gives a whole concept about how to estimate the sample size. Now, this is the plus or minus 2 standard error. Totally 95% confidence interval cover 4 standard errors. So the one side, it is 2 standard error. The 2 standard error concept is called the precision of the estimate. How precisely you wanted to estimate that the mean blood loss or HIV prevalence or hepatitis B. So therefore, this is sometimes we call it as allowable error. How much error you wanted to allow when you estimate the statistics? This is a question. So 2 standard error, please remember this is not standard deviation, this is standard error. We are talking about the variability of the means, therefore it should be measured by standard error. So 2 standard error is equal to precision or allowable error. If you do a little bit of modifications, the formula, you would get this equation. That is your 95% confidence interval limit and the variability of the data which you have. So this is, you have to have the variability data without which you cannot study sample size. This is the precision, how precisely you wanted to do. They said in our hospital, it is around 1,250 ml blood loss. Then you ask them how much is the variability from person to person, patient to patient. Say 100 milligrams. So 100 milligram is your SD. Now, how precisely you wanted to study this one? They say, how much error would you allow to this to vary? You wanted to estimate very exactly, then he said, yes, I would allow 50 ml to be varying or 100 ml to vary and so on. So you have the precision, he wanted to say if it is 1,250 ml, It could be 1150 ml or 1350 ml. So he's attaching 100% error on both sides, variability or precisely wanted estimate, or 50%. So substitute these values and estimate the sample size. Similarly, you could do this for the proportions as well. So this is, I'm not going to talk to you because in the interest of time that this is how. What do I mean by precision? This is 2 times, 1.96 times the standard error. It's called a precision or allowable error. That this has to come from you. It is related to the magnitude of the problem. So for example, what is the error which we are talking about? So I'm saying I'm interested in studying the prevalence of STD, which is said to be about 5%. What kind of precision can I give? Can I give 4% as precision when the problem is 5%? Or should I give 1% as precision? What does it mean? If I say 4% precision, the middle value is 5%. It could be 9% or it could be 1%. Almost you are saying, one hand there is no STD, another hand there is a very wide STD, very highly prevalent STD. So therefore, you need to be very careful in deciding what is the error or precision which you are talking about. It comes by discussion and consensus. Supposing the prevalence of violence at home is 25%, what could be the precision? So say 5%, so it could be 20%, or it could be 30% and so on. So it is relative to the magnitude of the prevalence of the problem. We need to be very careful in deciding. This is the same question which was asked in non-inferiority trial. What should be the ideal margin? Non-inferiority margin. This is for the beginners, that this is not for the seniors. This is the formula for PQ. This is 1.96 or 2 square 4. P prevalence of a problem. If the problem is 25%, this is Q is 75%. And how much is the precision or error you would like to allow? Substitute these values and get the standard sample size estimate. I'm just skipping that. This is to or use the slides to follow the formula, because a lot of youngsters are making mistakes while calculating sample size. Now, coming to hypothesis testing, this is not about estimating the quantity. This is testing. The one is better than the other. So you have two kinds of problems generally. One is the outcome is measured, say mortality, the mean hemoglobin of the two groups, and so on. So therefore, you wanted to see which one is better, which drug is better in terms of less mortality, or which group is getting a better hemoglobin level, and so on and so forth. So this is a bit tricky one. This is not easy. You don't talk about the estimation concept here. We set the null hypothesis here. Null hypothesis is usually say when I compare two groups. Say, for example, if the question is to study whether the incidence of tuberculosis is higher in high-dose cyclosporin as compared to low-dose cyclosporin. So you have two arms, high dose and low dose. What is the question? The question is which arm is the high dose arm is getting a higher incidence of tuberculosis. So if yes, then I would not go for high dose cyclosporin. So we're comparing two regimens and see the outcome is incidence of tuberculosis. Okay. In the process, we set up a null hypothesis. We say there is no difference in the incidence between two groups. So incidents are expected to be same. Now, why should we do it like that? Somebody asked me, why not there is a difference as null hypothesis and no difference as alternative hypothesis? This is what we are going to discuss soon in the non-inferiority studies. So to go with the hypothesis, that is, we always assume that there is no difference, that somebody asked me that why not reverse the hypothesis and so on. We'll discuss about it. If we wanted to show that all the crows are black, and I say, since my childhood, I have seen 100,000 crows, all the crows are black, therefore all the crow is black. That doesn't work anyway. So in order to show all the crows are black or not black, so you have to find one white crow. Find one white crow. That means the concept revolves around that the philosophy is easy to disprove than prove. What does it mean? If I find one white crow, then you would say that all the crows are black is rejected. So therefore, always you set the null hypothesis of no difference, find some evidence, there is evidence, then you reject the null hypothesis. That is how it works. Now, because I have not found a white crow, doesn't mean that all the crows are black. You cannot accept the null hypothesis. This is a very, very important concept. You will never and ever accept the null hypothesis. We will discuss it as we go ahead. So this is basically that the whole concept philosophy derived from the Portofla, and we are using this. So this is what we are going to discuss. 1960, someone found a white crow, and so therefore that hypothesis was rejected. So you see the white crow, I found it very difficult to get this slide for many years. And this is, now, this is, let us explain this. I said, when you compare studies, that you don't talk about confidence interval, we talk about errors, alpha error and beta error. Let us look at this 2-by-2 table very carefully. As I talk, you would assume that you have understood completely. After the class, you tend to forget about it now, or it's going to confuse you. So let us assume that there is a reality, truth, and this is a researcher's decision. The researcher confirms that null hypothesis is true, no difference. No difference between the two arms. So you're saying you should not say one is as good as the other one. As it stands, there is no evidence to conclude that they are different. In reality also, this is true. So therefore, you agree with the reality, and therefore no scope for error. On the other hand, the null hypothesis is rejected by the researcher. So you're saying that there is a difference. One is better than the other one. And in fact, it is not. Statistically speaking, that rejecting the null hypothesis when it is true means there is no difference, but you have said there is a difference. That is called alpha error. Please remember, this is very serious error, and therefore we keep it very low at 5% level. On the other hand, here you said there is no difference between the two arms, two groups, but in reality, there is a difference. There are many stories about this error that you have, the treatment is effective, but you have said the treatment is not effective, and that is called type 2 error. Many of you know that the streptokinase was useful for the myocardial infarction. The patient who developed signs and symptoms of myocardial infarctions, they're brought to hospital. There is a drug called streptokinase. The drug was available for many, many years. There are small studies which have not shown that drug was very effective, because those days people don't decide sample size and do the study. Then Dr. Salim Yusuf, friend of our England, and is a head of population research at McMaster University, St. John's Medical College graduate, is a cardiologist. He did the first meta-analysis and proved that streptokinase was very effective. Until then, there was no studies to show that it was really effective, and so on. After this Lancet paper, that people started using it very much. In every hospital, it is available, saves life. The point is, there are many studies that there are differences. Okay, there are differences between the two arms, but because people have not studied enough number, they were not able to show it is statistically significant. This is very important. So therefore, the question remains to be answered is it really no different? Or have I studied less number? Is it because I studied less number, therefore I am not able to show this is statistically significant? When someone says that no difference, immediately you should ask the question. Please work backwards. Do retrospective power calculation of the data. Another point should be remembered at this level. The power analysis comes after the study is over. So after the studies, generally people say mean power analysis means sample size calculation. Power analysis is done only after study is over and the study did not show any difference between the two arms. That is where we call is power analysis. Please don't ask power analysis once you have rejected the null hypothesis. Once you have said there is a difference and the p-value equal to less than 0.05. So please, this is where a lot of people confuse everybody without knowing the basic. On the other hand, the power. Power is what? When there is a difference. Researchers said there is a difference, and the reality also there is a difference, and you have said that it is my power is 80% or 90%. What does it mean to you? Let us understand what is alpha error in English, beta error in English, and power in English. What is alpha error? What is the probability that the difference shown occurred due to chance? So what does it mean that we write p less than 0.05? What does it mean to us? Say, for example, I say after my study, oral contraceptive use in women was associated with myocardial infarction. So p less than 0.01. What does it mean? That results could have arisen because of chance error, by chance alone, 1 in 100 times. Okay. Still, I don't understand what is chance. And in simple English, it means that this statement may be wrong. I'm saying the oral contraceptive is associated a risk factor for myocardial infarction. This statement could be a mistake, could be a wrong conclusion, 1 out of 100 times. So otherwise, the complement is over 99% of the time that I am saying that oral contraceptive is a risk factor. So therefore, this is, we use the word chance. It is basically, it means that this conclusion may be wrong 1 out of 100 times. This is very simple English. So what is a beta error? Beta errors, remember the streptokinase example. It was there was a difference, but they were not able to show any difference, statistically significant. If a true difference of stated magnitude existed, but the study would not have picked it up statistically significant. There is a difference, but the study is not able to pick that up as statistically significant. It is called a type 2 error or beta error. So the beta error maximum allowed is 20%. So you should not have 30% beta error, 40% beta error, and so on. So on the other hand, the power is the complement of the beta error. Probability that if a true difference of stated magnitude existed, that means there is a difference available in the data, the study would not have picked it up as statistically significant. So that is called beta error, a power analysis. If I come out with a negative result, no difference between the two arms, but there is some difference available. How many times the difference could be shown as statistically significant? 60% of the time. But the minimum needed power is 80% international standard. So therefore, it tells you that you should have studied some more number to bring that power to 80%. There are other measures. The main concept is about number. So therefore, that is called power analysis. I reiterate this fact again. There is a difference, but the difference was not shown to be statistically significant. The question is why? Because you have studied less number. What is the power? Do the power calculation. Then if the power is 60%, what's 20% more power you need. So therefore, you should have studied some more number to raise this power to 80%. Have you done that? Then you would be able to show a statistically significant difference. These are all the basic concepts, alpha error, beta error, when you compare two or more groups. So we are going to now onwards talk about testing hypothesis problem. So therefore, the power analysis, when do you do the power analysis? If the study is negative and you do not find any difference between the two arms, then you do power analysis. If the difference is already significant, then you do not ask the power, or power is expected to be more than 80%. Many of the older people, that they look at the number and they comment saying that looks like the number is very small. You do the power analysis. Okay. It is not because number appears to be small, you don't do the power analysis. You will have to tell them that the result is already significant. It doesn't need power analysis. Okay. So this is, if you look at the biochemistry, pharmacology, they all deal with 6 animals, 4 animals, 5 animals. Still they come out with a very high p-values. Would you say that the power is less? You don't say that. If the result is significant, you never ask power. The result is not significant, you need to ask power. Now this is, I'm using a Kant slides to explain that sample size is a function of alpha and beta errors and the difference which we are talking about. So this is the 95% confidence interval concept of the differences. Now we are now slowly we are going into confidence interval approach. We don't deal with the p-values now. Now this is the null hypothesis related data. This is the alternative hypothesis related data. And this is alpha by 2. Alpha error belongs to the null hypothesis and beta error belongs to the alternative hypothesis. Alternative hypothesis is rejecting the null hypothesis. Alternative hypothesis is related to rejecting the null hypothesis when it is true. Now, this is power. So this is power. As I said, the power is associated with the alternative hypothesis. Now, this is power. This is the beta error. This is power. When the two distributions are different, two samples are different, then you would say that power is very high. Now, this is power is a function of a few things. Now, this is, if an example, the low power, because low power, why low power? The mean difference is close to each other. Mean difference is very small. Two distributions are close to each other. Therefore, the power is low. As the mean differences increases, the power increases. So therefore, involving the data of the differences, that you would be able to say that it is going to be significant. This study needs less number, and so on and so forth. They're distinctly far apart, then the power is expected to be very high. So therefore, the difference, the main difference or difference in proportions are need to be looked at, and that tells you whether you are going to have a less number or high number. This is about the variability, that you standardize your difference. If I standardize my difference and look at the variability, the power is very high because there's a decent variability. This variability is very high because I standardize the difference, but when you look at the power is reduced, you see here, the power is less as compared to this scenario. This is, the variability is very less. The two distributions are very narrow, standardized to the difference, the power is increased. See the blue color, this is very high. So therefore, that if you have a very small standard deviation, narrow variability, the power is expected to be very high. So therefore, as you see here, the mean difference in proportions, and the variability are important entities to decide your number. Now, this is, I'm not going to teach you, this is for the beginners who do not have access to calculators, use this formula correctly. I think this is correct. Now, this is as an example to show plug-in numbers and see what is the number which you're talking about. And similarly, when you have a mean and standard deviation, then how do you calculate sample size? So I'm not going to do this one. Now, these are all some examples. Now we are coming to what Kant has started with the superiority trial. In the superiority trial, the hypothesis is one is better than the other. That is what it means. But you don't fix any margin to say that, because you say one is better than the other, but you say take the difference and see whether it is significantly different from zero. So therefore, the goal is to show that the effect of one treatment is on a certain endpoint is superior to that of another. The sample size calculation, that we say what is the difference, and to show this difference is statistically significant, what kind of number I should study with the minimum alpha error and minimum beta error. That is a concept which you do. So therefore, please, I wanted you to remember this equation. It looks to be, appears to be very easy, no difference. The difference is 0. Alternative hypothesis, the difference is not significant, greater than 0. The difference is greater or lower than 0. This is what it is. So the null hypothesis is that no difference. Alternative hypothesis, there is a difference. What is happening in research? If I don't reject the null hypothesis, please remember, if I don't reject the null hypothesis, okay, that is your all, if you don't reject the null hypothesis, that people accept the null hypothesis and say they are equal in effect. This is a very dangerous mistake that everybody makes. So if you do not reject the null hypothesis, don't ever accept the null hypothesis. Please take, this is a very important message that you get. When you say difference, that you know there is a magnitude to that difference as a small delta. Okay, you are saying that this is my delta, that this is this delta is greater than 0. So we don't do this only in the when you fix the delta is fixed only in a placebo arm control trial, because that in the placebo arm control trial, that we say there is a placebo effect that has to be taken into consideration, and you should not assume that difference is 0. The difference is attributed to the placebo effect. Therefore, whatever I get should be greater than delta. I'm not going to cover that part, though it is available in the McMaster software. Now, this is what Kant had shown you as a slide. So establish a 95% confidence interval for superiority trials and see whether it avoids 0 in between. The lower limit avoids 0 in between. So therefore, if yes, then you say it is statistically significant. You don't worry about the upper limit at all. So it avoids 0 in between, therefore it is statistically significant. And the minimum p-value is 5%. So now if you look at this one, that it includes 0 in between, the 95% confidence interval for the differences. Please remember, difference, it includes 0 in between, therefore it is not statistically significant. You don't worry about your upper limit. Now, I wanted you to remember this. This is the formula. The difference is the delta. The difference between the two arms is put here. This is where that the superiority trials are different from equivalence or non-inferiority trial. Please remember this. I will show you again the slide. What is this slide? And as against the slides which I am going to project. Many times there is a misunderstood concept by epidemiologists that equivalence trials and non-inferiority trials are supposed to give you very large number. That is because they think that these guys are looking at a very small difference, therefore the number should be much higher. This is a misunderstood concept. So I'll tell what are we looking at in your non-inferiority and the equivalence trial, not the absolute difference between two treatment arms. This is for the proportions. I'm not going to run through the slides, but you see that this is a very important assumption which we take. Many times in the hospital setting, people are using standard of care treatment. And this has been going on for a few years in your hospital. Therefore, they know the variability of the outcome. Here it is 40. Please remember the t-test, that when you want to compare two means, the variability has to be similar between two groups. You go by that assumption. You don't know the variability data of the new intervention which you're talking about, but I assume that has to be 40 as well. So otherwise, I cannot do that comparison between the two arms. To begin, I would assume that the variability in the new arm is as similar, as good as the standard deviation of the current or standard of care treatment. This is then you negotiate. The standard of care arm this is the mean, and you could negotiate and put that value as the mean difference here. You can't be doing all the time pilot study and data from other literature and so on. So you need to go by your own assumptions at some time and fall on assumptions of t-test, etc., regressions, etc.